Good morning, everyone. I'm Olivia Chapla, Astrobotic's Director of Marketing and Communications, and welcome to our Telecon for Peregrine Mission 1's Review Board. We appreciate your inquiries, and for some of you, your patience, as we comprehensively investigated and assessed each aspect of the mission. At the conclusion of this call, a report of Peregrine's Review Board findings will be published at astrobotic.com/press. We will also be sending out an e-blast to all of you. Now, today's briefing will serve as an informational session concerning the Peregrine spacecraft's in-space journey, our approach to investigating and assessing the mission's anomaly, and a path forward for future missions. Experts joining the call today from Astrobotic are John Thornton, the founder and CEO, Sharad Bhaskaran, Mission Director for Peregrine Mission 1, Steve Clark, Vice President of Landers and Spacecraft. Also joining us today is Dr. John Horack, Professor and Neil Armstrong Chair for Ohio State University and the Board Chair for Astrobotic's Peregrine Review Board. First, we'll start with some initial remarks from our briefers before taking questions. To add your name to our question queue, please message the Zoom call's Q&A box with both your name and your organization. And now we'll start off by hearing from Astrobotic's founder and CEO, John Thornton.
Thanks, Olivia. Just to review first that this was Astrobotic's first mission. Peregrine was flying and attempting to land on the surface of the moon, the first mission that took off and launched from Florida under the CLPS initiative. Launch occurred on January 8th at 2:18 a.m. on the ULA Vulcan launch vehicle. It was a beautiful, beautiful flight. So exciting. It was a real high to get to that point, to have so many years of work and effort culminating in that moment on that launch, and to see it successfully fly was truly thrilling. Once we were in space and released from Vulcan, we started to initiate our spacecraft. We turned on the avionics and the power management system and established communication with Astrobotic Mission Control via NASA's Deep Space Network, and that all was successfully accomplished at around an hour after launch. And then the next phase was to start commissioning the propulsion system. So Peregrine, excuse me, Peregrine's propulsion system was activated. This involved pressurizing the fuel and oxidizer tanks with helium from the pressurant tank by opening two pressure control valves. We're going to call those PCVs for the duration here. So PCV1 and PCV2 are the two pressure control valves that control that helium. Upon actuating, opening, and closing the PCV2, helium began to flow uncontrollably into the oxidizer tank, and that caused a significant and rapid overpressurization of the tank. Unfortunately, the tank then ruptured and subsequently leaked oxidizer for the remainder of the mission. Shortly after the event, the team was able to stabilize the spacecraft, and that was quite challenging because the ACS was not designed for that kind of impulse that we were getting from the leak of the tank. But we were able to stabilize, and then we were able to turn to the sun, charge the batteries, and proceed with the mission. We were able to gather the prop data through the course of the subsequent next days. We were also able to turn on payloads and power every one of the powered payloads that were on board the mission. And we got a tremendous amount of data and information about how the spacecraft flies, as well as all of our payloads in the orbit environment. So we obtained a lot of data about our systems and advanced the TRL system, TRL ratings for multiple parts of the subsystems of the lander. And ultimately, this lander is capable of flying in space, and that's a really, really big accomplishment for the team. As we all know, ultimately, the malfunction did inhibit our ability to land on the surface of the moon. We just didn't have enough fuel and pressure needed to land on the surface. So all in all, we operated about 10.5 days in space. We traveled more than 535,000 miles. Since the conclusion of the mission, there's been 2 science teams that have published science data from the science that was actually collected while the payloads were operating. And we understand that a 3rd team intends to publish imminently relating to radiation environment. Around the mid of the mission, we were deciding what to do with the spacecraft, and in consultation with NASA, we made the very difficult decision to return the spacecraft back to Earth for a controlled re-entry into Earth's atmosphere. We landed at an open spot over open water in the South Pacific on January 18th at around 4:04 p.m. Eastern. After the conclusion of the mission, we quickly assembled an expert board. We did that very quickly to make sure that any knowledge that wasn't written down already was at everybody's fingertips. We recruited Dr. John Horack, who was on this call and graciously has joined us here to lead that effort. And we took a look at ourselves, took a look at all of our processes, the technical side, and we're going to hear some of those results imminently here. So back to Olivia.
Thanks, John. And next up, we'll hear from Dr. John Horack, professor in Neil Armstrong Chair for Ohio State University and the board chair for Astrobotic's Peregrine Review Board. John, you're on.
Well, thank you, Olivia. Yeah, thank you, and good morning to everyone. Thanks for joining. My name is John Horack. I currently serve in the position of the Neil Armstrong Chair at Ohio State, which is a joint appointment between Mechanical and Aerospace Engineering and the College of Engineering and the John Glenn College of Public Affairs, a job I've had the pleasure of having since 2016. A bit of my background, some of you have had a chance to work with before, or at least communicate during the time I was at NASA. My professional career in spaceflight started in July of 1987 at the Marshall Space Flight Center in Huntsville, Alabama. Spent 17 years at NASA in two separate stints. The first stint as a PhD gamma ray astrophysicist and helped build a satellite called the Compton Gamma Ray Observatory and lots of other work. I left to start a software company. I did that for 5 years. I went back to NASA, ran the Science and Mission Systems office at NASA Marshall, which was an SES position. I then went to become the vice president for research at the University of Alabama in Huntsville, did that for 4 years. And then prior to coming to Ohio State, I served as the vice president for space systems at Teledyne Brown Engineering, where I had P&L responsibility for the space work that was done at Teledyne Brown. So it was an honor to be asked to serve as the independent chairman of the Peregrine Review Board. That review board was nearly 36 people, I believe 35 people in total, 26 of whom were internal multidisciplinary subject matter experts who knew the Peregrine hardware and the vehicle better than anyone else. We also had 8 external volunteers and private contractors who came recommended by NASA and other members from our space industry networks. So I had the chance and the pleasure of working with the team. I spent a number of days in Pittsburgh in person on several trips, working as they analyzed all the data, both from the flight itself, but also all the data leading up to the flight, qualification testing on various components, results of environmental tests, and then also after the space flight itself to go through the data. This was a very rigorous review process. The team used a root cause analysis method called causal condition methodology, which is consistent with industry-wide aerospace standards in terms of how you get to the bottom of why something happened. John Thornton described what happened, but the question is why. And after an extensive review of the events, before, during, and after the mission, the board concluded that the most likely cause of the malfunction was indeed a failure of a single helium pressure control valve, John mentioned, called PCV, pressure control valve 2, within the propulsion system. And PCV2 suffered a loss of seal capability that was most likely due to a mechanical failure in the valve caused by vibration-induced relaxation between some threaded components that are inside the valve, so a failure deep inside the valve itself. Now, among the many reasons that the board came to that conclusion is that the spacecraft is always talking to you when it's flying. It's sending back large amounts of telemetry, things like temperature data, roll rates, which tell you not only where is the spacecraft pointed, but how fast is it rolling around any one of the 3 axes, tank pressure data, and other things. And these telemetry data pinpointed both the location and the timing of the mission anomaly, which coincided with the position on the system of the pressure control valve itself and the autonomous sequence to open and close the PCV. So the spacecraft data were very consistent with a tank failure near the top of the tank. And as I said before, the PCV2 loss of seal capability was due to a mechanical failure in the valve. So I'll stop there. I'll hand it back to you, Olivia, and we'll be looking forward to your questions after a few other comments. Thank you.
Thank you, John. Next up, we have Sharad Bhaskaran, Mission Director for Peregrine Mission 1.
Good morning, everybody. This is Sharad. I'm the mission director. I've been the Peregrine mission director for 8 years, starting really when we began the requirements review for the program. Prior to Astrobotic, I was with Lockheed Martin working on shuttle, NASA Mir, and space station programs. So to confirm, we replicated the failure mode, the valve failing to seat, or still properly through terrestrial testing. We did with the spare flight PCV. We subjected to similar flight conditions. We subjected the valve to qualification level, shock and vibe, pressurized cycling, and a final seat force, and measured the internal leak rate. After cycling under pressurization, the spare PCV began leaking at a rate that was roughly equivalent to that observed during PM1 space operations. We disassembled the valve. We showed that the threaded joint on the valve was loosened, and an O-ring in the valve had been damaged along the sealing surface. So, adding here some context is what led to us selecting this particular component. In July 2019, after we won CLPS TO2, we made the decision to outsource the propulsion systems development to an outside vendor. We did go through a competitive selection process, and they executed a spaceflight proven process with industry standards in development. But in fall 2021, as COVID was affecting supply chains, they were suffering some schedule issues and technical issues, and these were compromising our mission schedule and really jeopardizing the next stages for our spacecraft integration and launch readiness. So in early 2022, we made the decision to pull the propulsion system in-house, partly assembled, and to complete it on our own schedule to give us more schedule certainty and confidence. By this time, we'd already made the decision to do Griffin propulsion systems in-house, the development in-house, to do more vertical integration. So we'd already developed a lot of the capabilities to do that propulsion integration. So we started doing that on Peregrine, or finished Peregrine with that. And this also burned down some of the risk going to the Griffin program, which is far more complex than Peregrine. As we were doing the assembly of the propulsion feed system through April and November of 2022, we started encountering issues with some of the components, in particular. The PCVs that you've already heard about were starting to have some leak issues. And so we continued to try to resolve the issues, but we already made commitments to go to acceptance testing for the spacecraft level, and of course, committing to launch dates. So in August 2022, we made the decision to pivot to an alternate valve supplier. And this is the same supplier that was already providing pyrotechnic valves for Peregrine. So once we put the new valves in and installed them, we conducted a final set of leak and proof tests on the propulsion system itself. This is where we encountered leaks with PCV1, which was the PCV controlling helium into the fuel tanks. PCV2 did not encounter any leaks at this stage. And so since PCV1 was easily accessible, we repaired it and passed the final round of proof testing. And then we completed assembly of the spacecraft, including what we call level 2 integration of all the elements of the avionics and electronics, and everything else was added to the spacecraft. And then we took the entire spacecraft through a rigorous acceptance test campaign: vibration, acoustics, thermal vacuum, and electromagnetic interference and compatibility testing. After all the testing, which was completely successful, we still carried PCV2 as a risk in our risk register because of the repairs that PCV1 had required during the proof and leak testing. But we deemed that the PCV2 failing was low, the likelihood of failing was low, because we had passed acceptance testing and it never experienced any leaks during that testing, PCV2. So we did identify the risk. Again, as I mentioned, we carried as low likelihood, but it's also the case that PCV2, as opposed to PCV1, was located much farther inside the spacecraft. And to access it, to do repairs or replace it, would have required extensive surgery on the spacecraft to take out key elements, large elements of the spacecraft, which would have invalidated the acceptance testing that we had just completed. And these are very time consuming and expensive tests. So that, along with the risk of doing damage if we had deintegrated and reassembled the spacecraft, led us to the conclusion that it was best to proceed to the next stage of the program and not to replace PCV2 and to proceed to flight.
Right. Thank you, Sharad. And a reminder, if you'd like to ask a question, please find the Q&A box at the bottom of your screen and submit your questions. We'll have Q&A in just a few moments. But first up, we are going to hear from Steve Clark, Astrobotic's Vice President of Landers and Spacecraft.
Thank you, Olivia, and good morning, everyone. For those of you who I haven't worked with in the past or talked with, I have about 40 years experience in the space and aeronautics communities, which is actually hard for me to believe at this point. But I started my career out at the Kennedy Space Center on the Space Shuttle program, worked in the Launch Services program. I had a 23-year career with NASA at Kennedy and at headquarters, working in human spaceflight, the Science Mission Directorate, and finally the Aeronautics Research Mission Directorate. So on top of my executive leadership and systems engineering program management experience, I have a background in spacecraft and launch vehicle systems, including propulsion. I came on board with Astrobotic a little over 4 months ago, and I'm really excited to be part of this team here in Pittsburgh. So I have to share with you, as soon as I came on board here, I got to know the team and found that we have a very committed and highly motivated team that is determined to make GM1, Griffin Mission 1, a success. They have their heads down coloring and working hard to make that a reality. And I'm very excited to be leading this team here to do just that. Talking about Peregrine Review Board findings that John Horack walked through, part of those findings also were corrective and preventative actions that were documented. And I'm helping the team take those lessons learned from Peregrine 1 and incorporating those lessons learned into the GM1 mission flow. And we want to do this obviously without disrupting the GM1 schedule. So we're doing this in a very deliberate way. We're also looking at process improvements, not only for GM1, but for all future missions. What do I mean by that? We're looking at various quality processes, procedures, technical drawing, release procedures, and so forth like that, where we're looking at streamlining those and making them more efficient. I do have a partner with that. You may recall that Frank Perry was hired in the same day I was in April. He is the Director of Engineering for Landers and Spacecraft. He has a 30-plus year career with NASA at Langley, and he and I have been doing a lot of collaboration on those process and procedure improvements. So I hats off to Frank helping us with that as well. Also, we've got Astrobotic personnel at various supplier locations helping to ensure that we keep on schedule. And they've also been providing some additional oversight to ensure a greater level of accountability and control. So as we move forward, we're going to continue to improve those processes. I also want to talk just a little bit about the valves that Sharad did a great job of walking through on Peregrine 1. So I'm sure all that are curious, what are the changes we're making to GM1? And so we have been working very closely with the vendor to redesign the pressure control valves to address specifically the mechanical sealing flaw that we saw on PM1. We have been testing these valves at the component level, and we've actually incorporated a couple of new components in the GM1 system. We've incorporated a pressure regulator upstream from the oxidizer and fuel systems. So what that does is that's one way of mitigating the single valve failure that we experienced on PM1. So for instance, if the pressure control valves failed in the similar way, this pressure regulator could be used to regulate the flow of the helium as a pressurant. We also have installed latch valves upstream of those pressure control valves as well. So again, if we did see the same failure mechanism on the pressure control valves, those latch valves would also be a way to control the flow into the oxidizer and fuel tanks. Let's see. So I just wanted to kind of go back to the corrective and preventative actions being implemented as Sharad went through. We had a total of 24 total in-flight anomalies on Peregrine 1. The PCV2 failure, which was what we considered a catastrophic failure, is handled as a failure. One could say that those were actually 25, but we handled that separately. Of the 24 anomalies, 8 were mission critical and potentially mission ending, but our excellent mission operations team handled those real time during the flight and resolved all of those. There were additional 5 non-mission critical in-flight anomalies. Those were also resolved real time during the flight. And then the remaining 11 anomalies were assessed and deemed minor, and we analyzed those post-flight and looked at those as corrective actions going into GM1. So just keep in mind, again, John Thornton mentioned this spacecraft flew successfully for 10.5 days in cislunar space. Although we weren't able to attempt a lunar landing, we were able to increase the technology readiness level of just about all of our other systems, including avionics, our power systems, RF communications, and GN&C. So we actually were able to do the actual acceptance testing in a real environment of cislunar space. And so now we bring those systems into Griffin Mission 1, and we've tested those already in space, which provides us good heritage moving into GM1. So for in conclusion, we have high confidence in our GM1 flow, and we are looking forward to launching GM1 no later by the end of next year. Olivia?
All right. Thank you so much, Steve. Well, at this point, thank you, Astrobotic team and Dr. Horack, for your comments today. And now we'll proceed to the Q&A portion. Now, for this to function, what you do is you add your question to the question queue by messaging the Q&A box at the bottom of your screen. Please include both your name and organization. And when it is your turn to ask a question, you will receive a request to unmute your mic. So please accept the request to unmute your mic for us to hear you. So you must accept the request to unmute successfully. So with that, let's start with Jeff Faust, Space News. You should be receiving the request to unmute now.
Yeah, can you hear me?
Absolutely.
Great. Question, I think probably for Sharad, as you went through that sort of the sequence of the valve replacement and testing and so on, did you do any testing of PCV2 after the spacecraft environmental tests? Cycling the valve, anything like that to see how it worked. And if you didn't, would such tests might have caught the problem before launch?
Yeah, so once we finished acceptance testing, we did operate the valves again, but not at full system pressure because we had to, we're still, we don't do the full system pressure until we go down to KSC and load the propellant, load the helium and all that. So we didn't do it under full pressure, operating pressure scenarios, but we did have a chance to test the valves again under lower pressure.
All right. Next up, we have Marcia Smith, Space Policy Online.
Thanks so much. Can you hear me?
We can.
So my question is, the technical root cause was the valve, but what was or were the other causes? Schedule pressure, inexperience, other administrative or managerial issues? And what lessons are you drawing from that for the future?
John Horack, would you want to take that one?
Sorry, we're having just a technical difficulty unmuting a mic. One moment. All right, John, you should be unmuted.
All right, thanks. Yeah, and good morning, Marcia. In working with the team, clearly, if you have a more robust piece of hardware with multiple valves in place, and I think Stephen Sherrod alluded to the changes that are coming for GM1, you could find a way to go forward. I really found that in looking at the team and in looking at what happened, there wasn't a point in the flow. You play the ground ball when it's hit to you. I would not have made any. I can't see any decisions that were made in the flow leading up to the launch where I would have said, hey, I think you should have done this differently. Every time there was a decision point to be made, perhaps a launch date moved or something like that, you go through a major environmental test. Those decisions were pretty sound. So I think the decision making of the team was very good. And so, really, I think this is a situation where you had a pretty unfortunate piece of hardware that failed in the valve. Unfortunately, the design was such that if that valve did fail and you overpressurize the tank, you have a very different mission with, in this case, loss of the opportunity to try to land on the moon. As far as what's going to go forward in terms of the team and other things, then I think Steve talked about that. But I was very satisfied in having looked through, the history, and actually I was there the day the valve test failed in Pittsburgh on the shaker table at pressure. Really, really happy about that. And I don't know that there were a lot of other mitigating factors that led to the valve itself failing. I take heart in the fact that, when they flew, the team saw several anomalies and fixed them on the fly. And so, going into GM1, I personally, as an independent set of eyeballs, am pretty confident that this team's going to be able to have a successful mission.
This is Sherrod again. Just to clarify a point on the valve testing, what I spoke to was the testing that was done after the spacecraft had gone through full system acceptance testing, and really after that point, that concludes the entire testing program, and really you send the spacecraft to launch for launch. But prior to that, in the development phase, the typical approach is to determine which components in the spacecraft require full acceptance and qualification testing at the component level prior to even integrating those into the spacecraft, after which the spacecraft itself goes through, as I mentioned, the leak and proof test of the propulsion system, and then the vibe, acoustics, EMI, and thermal vacuum testing. So we did do component level testing prior to integration onto the spacecraft. And part of the decisions in which components we choose to take through a full acceptance qualification program versus which ones we don't is really based on risk. And in this case, we determined the risk of that particular PCB2 was low because it hadn't failed through any of the testing programs that we had gone through. But it's also influenced by cost and schedule, and so that's how we made the decision to leave PCB2 as it was.
Thank you, Sherrod. And a reminder, if you'd like to submit a question to the Q&A, please find the Q&A box at the bottom of your screen and submit your name, and we'll get you in the queue. So next up, we have Anthony Colangelo, main engine cutoff.
Hey, thanks. Trying to make sense from the post-mission report of some of the timeline when it seemed like a series of things happened. You stated that you worked with the engine vendor to theorize that you could use the engine in this state with short pulses, but you also found out the trajectory was impacting Earth around the same time, which ended up being the safest option, but you did then still use the system quite a bit to move the impact point, even though using the system was a risk that was identified by the mission. So I'm just trying to understand, it feels that portion feels like a little muddled to me in terms of what order things happened in and how you got to the decision to make use of the system, even in this state.
Yeah.
I don't know.
Hey, Anthony. Yeah, I can speak to that. So we did, the mission was planned as to have one phasing loop going to lunar distance and then coming back around Earth before the final approach to the moon. we were having some challenges understanding the trajectory because of the leak and its impact on our trajectory itself. And we had not fired the main engines in the early parts of flight because of the leak itself and the subsequent high mixture ratio that would be applied at those engines. When we reached apogee, we started and lunar distance, we started gaining more understanding of where our trajectory was taking us, and we realized that it was the leak had perturbed the trajectory to where we would actually be impacting Earth as opposed to a 1,500 kilometer perigee that we're predicting based on mission design. So at that time, as John mentioned earlier, we consulted with NASA and made the decision that we would go ahead and do a controlled reentry. Based on what our prediction was of where the spacecraft would re-enter, we decided to try to fire the main engines to alter that reentry point, and we did consult with the engine developer. And of course, at this point, the mixture ratio of fuel to ox was going to be extremely high, which would way beyond the design limits, and so that would result most likely in the engine failing due to high temperature. But we did talk to them and found that we could do some quick pulses, which would prevent the engine from overheating very quickly. And so we executed those quick pulses. The GNC and nav teams and propulsion teams all worked together to determine how many it would take to alter our re-entry point again over the South Pacific into a clear zone. So we executed those burns. After each burn, we would check the temperature of the engines and let it cool down before we executed the next pulse. And out of that, we got a fair amount of delta V that, again, allowed us to re-enter at a certain point into the South Pacific.
And to clarify one point on the timing, this is John, is around lunar distance was the time that we were figuring out what to do at the conclusion of the mission. So we were looking at, can we do a delta V burn now and avoid Earth, or should we let it go into Earth? So at that time, that's when we had established the procedures of doing short pulses for the burning. So we had the data then. We felt like that could be a path, but ultimately we made the decision to come back to Earth for a safe reentry.
All right, thank you so much. And next up, we have Stephen Clark from Ars Technica.
Hi, thanks for doing this. Stephen Clark, Ars Technica. I think my questions, can someone kind of compare the propulsion systems on Peregrine and Griffin? I know Griffin is a much bigger spacecraft. Any differences in their architecture between those two systems? And are there any more of these pressure control valves needed in that system, or is it just these two, same number that was on Peregrine? And yeah, and I think that's my main question. Just kind of compare the complexity of the two propulsion systems. Thanks.
Hey, Steve, this is Steve Clark, your alternate. Good to talk to you again. So yeah, the system on Griffin is different than Peregrine. It's a larger spacecraft. It's a more complex spacecraft because it was designed to take heavier payloads. I think I mentioned earlier that the changes we made to the system is, of course, we have additional oxidizer and fuel on board Griffin since it's larger. What we incorporated into the feed system design on Griffin is the regulator that I mentioned upstream from the oxidizer and fuel tank pressure control valves. And again, to eliminate the risk of that single point failure that we had on Peregrine. And we also incorporated what we call latch valves just upstream of each of the pressure control valves, one on the oxidizer side, one on the fuel side. Again, these are dissimilar valves, but they provide protection against that fault that occurred on Peregrine 1. So we've actually improved the reliability of the propulsion system on Griffin, larger tanks, longer feed systems, obviously, because again, it's a larger lander. But we've got increased reliability now in the system to mitigate against that single point failure.
Perfect, thank you. And up next, we have Evan Robinson Johnson from the Pittsburgh Post-Gazette. Evan, you're on.
Yeah, thank you guys so much for hosting this and taking questions. Sherrod, I know you said the valve was a known risk. Did the review board in its assessment conclude whether its failure was the result of how it was made, by the supplier, or kind of that pre-flight list of actions that Astrobotic took?
So it was a combination of design factors and testing. As Steve, I think, alluded to, the valve is undergoing changes for the Griffin mission to be more reliable. But did I answer your question?
Evan, we're going to put you back on to make sure we answered your question appropriately.
Yeah, all good. And just I guess the second part was like with all of those changes that you've made, I mean, there's still concern about valves, right? And just wondering what the likelihood is that we could see a very similar failure of a valve with Griffin.
This is Steve Clark. We have been working with the vendor to redesign that valve, which we've done to address the particular seating issue that John Horack went into detail on, and I think Sherrod touched on as well. So the internal design of that valve has changed, and we worked very closely to mitigate that same failure mode again to ensure that the valve will reseat whenever we cycle that valve. So we think we're in good shape there.
And to add to that a bit more for Griffin, it is this is John. It is a single fault tolerant design for Griffin. So that means that if that valve were to fail the same way as Peregrine Mission 1, there is a backup system that would be able to control the helium. That is the latching valve that we added. In addition to that, we even get additional control over the helium pressure from the regulator. So we've got one fault tolerant and really like a little bit of extra support from that pressure regulator.
Thank you, John. We don't have any other Q&As in the queue box. We just did. So Marcia Smith, we're about to unmute you and you can ask your question.
Thanks for giving me a second chance. And I just wanted to clarify, so the valves on Griffin are the same valves as were on Peregrine, but you've added these regulators upstream to prevent the overpressure, is that correct? And also, who is the vendor? And are there any more flights of Peregrine planned?
Wow, all good questions, Marcia. This is Steve Clark. I'll address the first one here. So the valves are different. As I mentioned just a minute ago, we have worked to redesign the internal workings of that valve to ensure that it reseats properly. So it is slightly different than the actual valve that flew on Peregrine. The same vendor, but we've worked closely with them to redesign the internal workings. And then, as I mentioned and John Thornton mentioned, we have the latch valves and the pressure regulator that will eliminate the single point failure that occurred on Peregrine. On your question about the vendor, we typically do not share, all the different vendors that we work with, just because we ultimately are responsible for the mission success. Astrobotic is. So on the third question.
Yeah, on the question about the future for Peregrine, will it fly again? We continue to pitch that lander for opportunities for future missions. One interesting scenario that we're looking at, because it's now proven as a spacecraft in cislunar space, is the potential for using it as a tug or using it as an alternate spacecraft bus. It's quite capable. It flew 10.5 days in space. Avionics worked, battery worked, solar panel worked, comm worked. The basics all worked, other than that valve failure. So we feel very confident that it could be a fantastic platform for future uses of other mission profiles.
This is Sherrod. I'll add that we're actively in talks with various customers to talk about those other types of missions that it could support. And given that we did operate for 10 days in space and we proved avionics, comms, power systems, and our flight software, all that hardware doesn't operate without a very robust and proven flight software system. So that demonstrates to us that this is a very capable spacecraft that can complete different types of missions.
Yeah, one last thing too, I'll say our mission operations team learned the hard way, but on the fly, and they're very experienced now on how to fly that spacecraft in cislunar space, even with an anomalous condition as well. So the team is well seasoned now.
All right. And just a reminder, if you're just joining, I saw a few people join near the tail end. If you'd like to submit a question to the Q&A box, you'll find that at the bottom of your screen. So up next for questions, we have Will Robinson-Smith of Spaceflight Now.
Hi, thanks so much for taking the time to speak with us. And forgive me if this was asked earlier since I'm hopping in a little bit late here, but regarding Griffin Mission 1 coming up here, has Astrobotic manifested some additional customers since Viper was taken off, or how much time, I guess, is left for additional customers if there's some further interest for them to be manifested between now and when that mission is hoping to launch? Thanks.
So we're working through that right now. We're continuing to, we have dozens of conversations about folks that have wanted to fly on Griffin. Some of those are more advanced than others, but we're in active conversation on that. I do want to point out that Griffin has active payloads already baselined, and the first is our own Cube rover with a payload from a partner called Mission Control, a Spacefarer in collaboration with the Canadian Space Agency that's going to be flying. So there will be a small rover on this vehicle already. And we're also going to be flying European Space Agency's LandCam X, a NASA laser retroreflector array, an additional payload that I wish I could talk about, which is way cool, but hopefully we'll be able to talk about it soon. Those are already manifested on the mission and were manifested prior to Viper's removal. Now we have extra payload capacity. We are in conversations with multiple parties, as I mentioned, for addition to flight by 2025. It's a short time frame. There's not a lot of spacecraft that are ready to go that can be bolted on, but we are talking to all of them about those options.
All right. Thank you. And up next again, we have Jeff Faust from Space News.
Hey, good morning. Question for Steve Clark. You've mentioned that there are 8 other mission critical anomalies during Peregrine's flight that were all resolved. I wondered if you could give any examples of those anomalies and how they were resolved and how they might affect the design or operations of Griffin.
Hey, Jeff, I'm actually going to kick this over to Sharad since he was the mission director and he's got much better insight. Sharad.
So Jeff, those they're a combination of flight software, GNC, and we had one anomaly with DSN itself. Those were resolved real time by the flight control team. They modified software in some cases. Some had to do with failure detection, isolation, recovery procedures. I can't go into too much detail without divulging too much about the spacecraft itself, but again, those were all resolved real time, and those have been all those lessons learned from those have been infused into GM1 as well.
All right. And up next, we have Stephen Clark again from Ars Technica.
Hi, thanks for taking another question from me. Us space reporters have been learning a lot about valves the last few months. I'm curious if someone can go into a little more detail about the actual, failure mechanism of this valve. What caused the sealing surface not to seal properly, and what is the material used in the sealing surface of this valve? Thanks.
John Horack, I think we're going to open up your line to say a little bit more on that.
Yeah, so the way I would think about this is, you've got, as we said, a threaded component inside the valve. So you can think about a screw and a washer or any threaded component. And if you shake it sufficiently, you can get some changes in the mechanical configuration that will prevent the valve from sealing. And it's pretty much no different than when your sink starts to drip in your kitchen. Water gets through the seal and comes out the other side. In this case, it's helium and it's high pressure, so it's much harder to confine. So we actually did, as I think was mentioned by Sharad, we took a spare flight valve, we shook it to qual levels, we then put helium on it, and after a moderate small number of cycles, the valve leaked, and you could hear it leak from about 4 feet away. As far as the design of the valve goes, let me turn that back over to Sharad so that he can give you some more information if that's permitted by the vendor and by the contract.
Thank you, John.
Yeah, this is Sherrod. Sorry, the details of the design is proprietary to that vendor, so we can't really speak to that.
All right. Up next, we have Anthony Colangelo again from Main Engine Cutoff.
Hey, thanks for the second round. Curious if you can give us any context with the CLPS contract itself, with the way the mission ended. Were there milestones that the team missed out on, or what percentage of those did you receive based on the performance of the mission?
Sure. So first is that each one of the CLPS missions that is awarded, there's about 10% of the milestones that are based on success. And in this case, for Peregrine Mission 1, there were a series of success milestones. We were able to collect, what would it be, 30% of that success fee. And that was because we launched, because we operated in space, because we commissioned the spacecraft and it worked in space. So we were able to collect some of those. The next milestone would have been, I believe it was orbit in lunar orbit. That was the next one that we were not able to accomplish on this mission.
All right. And next up, we have Kenneth Chang, New York Times.
Great, thank you. I was wondering, what is the key mistake here, or is there a key mistake? So I was wondering, like, if you could jump in a time machine and sort of redo the decisions based on what you knew then, is there a point where you should have made a different decision? Or is this the level of risk we should accept for a lower cost mission? Thank you.
All right, we're going to open up John Horack's mic. 1 moment.
Yeah, Kenneth, good morning. Thanks for the question. I'm looking forward to joining you when the Cardinals, my St. Louis Cardinals, play the Yankees later this weekend in New York. As far as decisions go, my assessment is no. I think the decisions that were made at each point in time were sound engineering decisions and sound programmatic decisions. If you're going to ask me what I wish we had, I wish we had a more robust design of the valve. And sometimes hardware just fails. And when a hard piece of hardware fails, you know, as was spoken about, PCV2 showed no sign of problems during the entire mission prior to the launch. There was no indication there was a problem with the valve. There was no indication there was going to be a problem with its seating. PCV1 had its issues. They are the same design. And Sherrod talked about why they decided not to go in and do major surgery on the spacecraft. I think that was a very sound decision. So, you know, sometimes I think you just, stuff breaks. And, you know, I'll leave it to John Thornton and others to talk about the nature of the design. But, you know, this is a lean forward, let's go fly kind of design mission. You know, and while we're new redundancy, if you will, or backup is being added to Griffin. You know, this is the Peregrine design. Had the valve not failed, I would have been very optimistic about being able to make some of those other milestones that John talked about, because the propulsion system, aside from the leak, you know, they were able to fly it. The comm worked, the battery worked, GNC worked. So this is, in my opinion, we had a piece of hardware break.
Yeah, and to speak to that bigger question about is this what we should expect for lower cost missions? I mean, we do have to keep it in context that this is not a multi-billion-dollar mission. This is a mission profile that is new, and it's a new form of it. And these are the first missions. It's a little bit like the first launch of a new launch vehicle in a commercial paradigm. How many times have we seen a first launch fail? It's part of the development cycle. It's part of how we learn. It's part of how we get better as an industry. Another way to think about it is if you asked you know, a storied player like JPL to land on Mars for 1/10 of the cost, they would have to make some tough decisions on risk and program as well. And that's basically what we're doing here is we're trying to do a mission at a price point that has never been possible before, and as such we have to make decisions on where to focus and how quickly we can get to launch. And we're trying to balance that. And I think we got really, really close. I'm very confident that Griffin we're going to hit the right balance, and we're going to stick that landing and be ultimately successful.
Great. Now, with that, John, do you have anything else to add before we wrap up the Telecon? Oh, wait. Oh, we have one more question we'll fit in. All right. Will Robinson Smith from Spaceflight Now, we're going to unmute you.
Hi, thanks for squeezing in the time for one more question. Just to follow up that statement from John, maybe sort of as a step back and look at the CLPS program overall, sort of given the information that you know now and the challenges of performing a mission like this at the cost or the funds that you get from NASA, you know, if you could redesign CLPS, do you think it would be wiser to, you know, put more money in each pot for each of the CLPS providers to, you know, not have it be such a tight squeeze? Or do you think that, you know, now having one mission under your belt, you're able to sort of think about, you know, the risk management and some of the ways to reshuffle priorities to make it a more successful venture given the constraints moving forward? Thanks.
I mean, first is that I think CLPS is very successful just unto itself. I mean, we have, what is it? I think 8 missions that have been manifested to fly to the surface of the moon. And that is just dramatic change. If you look back 5 years prior, there were no missions manifested to go to the moon at that point. So it's a dramatic success in that case. I can tell you from a vendor perspective, if there were multiple missions manifested at the very beginning, that would have helped create more stability and I think improve the building up of the supply chain. But you know, given where we are with the CLPS program, we have made great strides with that, and I think the arrow is pointing in the right direction. I know NASA is already thinking about CLPS 2 and upgrades for the next version of CLPS, and I'm optimistic that we're going to have a really bright future for the CLPS program. Steve Clark, I don't know if you want to add anything to that.
Yeah, so just for a little background, I guess I was at NASA when we started this CLPS initiative, and certainly it was, I would say, a lean forward by NASA and to help jumpstart the commercial lunar ecosystem. And I think it has done just that. I think, as John said, 8 task orders have been awarded, which is fantastic. As you move forward with a new initiative, though, you get lessons learned as you go along the way, right? And I know we have talked with the CLPS project office, as the other CLPS vendors have as well, to provide them feedback on perhaps how to shape CLPS 2.0 to make it even more successful. I think NASA has learned a lot in these last 5 years, and certainly the CLPS providers have as well. And I think we'll come together on how to shape CLPS 2.0 to help both NASA and the industry move forward in a successful way. But I'm particularly excited watching not only Astrobotic but the other CLPS providers get these awards and take the opportunity to provide low-cost commercial lunar landing services to the nation. And so I look forward to seeing how the rest of this year and next year, not only Griffin Mission 1 next year, but the other providers as well, because I see a bright future for commercial lunar economy. We're at the very start of it. NASA's done a great job with industry on commercial LEO moving ahead. And so now we're part of the next step on the lunar economy. So I think it's all good. I think we're moving in the right direction, as John said, the arrow's pointing in the right direction.
All right. And John Thornton, do you have any other thoughts before we wrap up our telecon today?
Yeah, I just want to thank everybody involved in the call today, especially John Horack, who volunteered his time to help us with the independent review team. I'm proud of the team for a really thorough review. I think it does look like the answer is really the right one for what occurred with this mission. I think we've learned a lot through the course of the mission and the review, flying it, with mission control, all of the pieces. This is how we learn. This is how we're going to get better as an industry. This is how we're going to get better as an individual vendor. And we're going to just keep focusing our development on Griffin Mission 1. Team is dialed in and using all the experiences and lessons learned from Peregrine Mission 1 to ultimately make Griffin a success. We are excited to be flying that next year. and can't wait for that euphoric high of a great launch once again, and the launch of another adventure out to the surface of the moon. So we're excited and really looking forward to our next steps here. And I think this is just the very beginning of an industry. As I mentioned, it's these first missions are like the launch campaigns. 5 years from now, we're going to be looking back and saying, oh, well, of course there was a failure or two, but now we've got this capability to fly to the moon for a fraction of what it would normally cost. And now we're talking about, okay, now let's build infrastructure on the moon. Let's build power on the moon. Let's build rovers on the moon. Let's go for the resources and help support astronauts. That's where we're headed. The CLPS program is getting us there, and we're excited to be a part of that story. So thank you again for everyone being a part of this the call today.
Thank you, John. And a reminder that the report detailing the mission and the review board's findings can be found on our website at astrobotic.com/press. If you have additional questions or you want to conduct one-on-one interviews with any members of our briefing today, please contact us at Astrobotic or press@astrobotic.com. We will also be sending out a copy of the report via email to everyone registered on this account and to anyone signed up to our email list. Thanks to everyone who submitted questions, and thank you to every briefer that joined us today to update us on the review board findings for Peregrine Mission 1. Thank you, everybody. Have a good day.